Hello, everybody. This video, I'm going to try to finish up everything about sorted list and begin talking about the next data structure, which will be Q. So to begin with, for the data structure sorted list, we've been looking at it for a while. You're doing a homework on it. What I want to say is that there are three implementations that I have written, three different implementations for this same thing. To make this work, I should have a main routine that doesn't change no matter what implementation I use. And that I do have, and I'll show it to you right now, as soon as I get it off where I have it hidden. Here we are. This is a main routine that opens my input file, reads the input file, however many I want. I have that's taken care of in the description of SList, prints it, and then times both the reading and the printing. And the second, well, it just times the printing in this particular case. So that's the same file. I don't want to change that, no matter what I do with the implementation. Now, the file needs a few things at the top that I plan to use with it. So I need my include files, and I need a few other things. And I'll show you those. I used fstream for the import string because the value is a string. iostream. Algorithm because I wanted to use the built-in sort for both the array and the vector. It would be faster than what I could write. ctime because I wanted to time it. And I decided to try 10,000 in this particular case. Those are going to remain the same. Now, SList is what is going to change. And here's the first of the SList. It's a pretty short one. And we'll take a look at this. This list is the array implementation. So let me put up here, this is the array. I got to write it down here. Array implementation. I just leave it as array. And I think what I'll do is I'll see if I can get it on one page. So I have the method. The way this is going to be, it's going to be string. It's going to be an array. So it's a string, an array of strings. Read in bulk is going to take in the items and just put them in the array. You notice I didn't sort them yet. Then after I read them all in, I did the sort. That is the built-in sort for an array. It comes from algorithm. ST is appointed to the beginning of the array, and ST plus index is appointed to the end of the array because I add every time I read something in. But as usual, I'm one ahead. There is no STINX. There's an STINX minus 1, and that's the way sort works. It goes to the one before ST plus INX. plist is simple. It's just an output. I have the is empty, which is the same. Is full, I just put it down for N. Now add to list, I didn't fill in. I filled that in a different program I wrote, which I will probably be coming shortly. Now that's one way of implementing it. But I can do exactly the same kind of implementation using a vector. So I'll show you the same thing using a vector. I got to get that over here. Just give me a second. I got to get the S list. Here it is. And I have it right here. There it is. And here I have it. Now, it doesn't look much different. In fact, this is the same. The only difference here is I have push back instead of reading it in directly as I did with the array. The sort, now there's a different way to get the first element. The first element of the vector is st.begin. And the last element is the one before st.end. Just as above, it doesn't include the st.end. And the difference here was vector equals st. Vector string st is the structure I'm using to represent it. Now again, I wrote this, and I don't have to change the main line, even though I changed the way it was implemented. Now finally, I'm going to try now unfortunately it's one line off, so I can get that. Wrong way. Okay, now I can start the new one here. And this will be the linked list. Now, for most of you, this is the hardest one. And I'd like to try to figure out how to get you to see that it really isn't that hard once you get used to it. So I'm going to show you the same way I did slist, only with the linked list instead. Now to do that, the first thing I had to do was I had to declare a node. So before I could do anything else, I needed a node. Then I could run the class. So we'll get the class up in a second. Now this seems to add more. Yes, this one was more complicated, but that's true. And so let's take a look. So first of all, instead of declaring it as a vector or as an array, I declared it as names pointing to node. So the inside is names, where up here, the structure that was holding everything was st. So that is a difference, but you notice they're both type slist. So the user has no idea that I changed things inside. I started as null, it's empty, and then I have read in bulk. Now read in bulk simply says, get in the string that you want to read. I passed in the file where the string was, and I made sure it came in as reference so it could change as things were done to it. I create a new node, new value, and then I read in the first value. While I'm not at the end of the file, I create the new node, put the value in. I don't have to put the null in because it's already there. And then I call add to list, and then I loop around again. And each time I read a new value, and I increase INX. So just as above, INX is how many there are. Now, plist is, you've seen this about 10 times, maybe more. It simply says walk down the list one by one. Start temp off at names, and then go print out what temp points to if you're not at the end. Move temp to the next one. I wanted to print out the number, so I put ++ there for the number. And keep going until you get to the end. So that one is, we've seen it. Now this was the complicated one, add to list. And this is something that you had to think about in your homework 3. Some of you are still doing it, I know. There's a special case. The first one has something different than the others. When I have temp and my second temp, when I have temp, the problem is that I'm always going to have names is not a node. Names is a pointer to a node. But when I have temp going down, I'm going to keep making temp pointers to a node, and they're going to have node structure. So the first one is different. What I do in the first one is say, if names is null, then I'm going to add it right at the beginning. Or if the value that I'm putting in, the value that I put in that node, that I read in, is less than the first value in the list, then I take the new node and point it to the first value of the list, and I have the name of the list point to the new value. So that takes care of the first case. Now the second, the general case. All right, temp is names. I probably could have done without that since I'd done it already. While temp.next does not equal null. If the new value is less than temp.next, that exists, value. So we're not looking at temp's value, we're looking at the value after temp. If it's less than that, the new val next, which is the new node, will point to what temp next points to, which has the value that is greater than what I'm putting in. And temp next will point to the new val. That puts the new val between temp and what temp pointed to. Otherwise, I keep moving. Now, it turns out there's another little thing to worry about. Make sure that you have the ending right. If temp next equals null, if I'm at the end of the whole thing, then I have to put new val next equal null, which I already had, I didn't need that. And then I have to have temp next, which is null right now, point to new val. So that's how I managed to put that in. Now I have 3 programs that actually do putting things in, searching, and deleting. I can't obviously give you all 3 of them right now, because if I do, you'll have homework 3. So instead, let me bring up what I have. think I may have to wait. Oh, here we are. Okay, I think I can get you at least the implementation, one or two of the implementations. No, I can't because I don't have them. So instead, I'll go over to Visual Studio and show you the implementation I have. I'll have the array one. I'm having a little trouble with my Visual Studio. It doesn't always seem to want to bring up what I want it to. But I hear you're having more troubles with yours in many cases. So we'll see what we can do here. I'm going to try. I can't. All right, this is the has at the beginning everything I've been talking about. This is for the solution using a string. And I increased the size of it because I wanted to put 500 more elements in. Now, what I did was the read in bulk has changed a little. Now it only reads n of the elements. But remember, that's still hidden from the user. And I did the same thing with the others. And all I did, I have a binary search when I'm searching for something. And here's the main routine. First of all, I read in bulk. That puts it in. And I time how much that takes. Next, I close that file and I bring in the toFind file, which is what I'm looking for. I pulled in 5,000 elements, brought each one in, and searched for it using binary search. And I told you whether or not it was there. And then I closed that file. Then I took in the toAdd file and I added some of the elements here. And what I did was I went down in the list. I didn't want the first 5,000. I wanted the 500 after that. And I did the add. Now I'll run this for you. You notice this file is 1,499. That means that I've added more than the first 1,000. If you go up farther, you'll see that just before that, I did the finding, the locating the items, and I said where they were. And then above that is the original after I read in everything. And it has 1,000 elements, I believe, which would be 999 because we started at 0. And there it is, 999. So those were the 3 items that I had there. I didn't have the delete in this one. I don't know why. I thought I did, but it appears I did not. Let me look and see if there's any chance I didn't notice it a minute ago. No, I didn't do the delete inside this one. The point of all of this is that there are 2 sides to abstract data types. One side is the user side, the person who uses it, and they don't care about how you implement it. The other side is the implementer side. And the idea is that we should be able to change the implementation without touching the user's code. And that's what I tried to do in these three. Now, either tonight or tomorrow, depending on how things go, I'll put out those three programs for you. They'll probably be on one file. And I will be able to say goodbye to the sorted list for a while, and you will be able to. Now, the next thing to talk about. Let me get rid of this. I got to get rid of that. And I want to get a blank file if I can help it. So I'll bring this over. Well, I thought I'd bring it over. Yeah, here it is. So, what I'd like to talk about next is the concept of a stack. The stack is also implementable in many different ways. The same three ways I think we can do the other one. So it's not unusual that we try it in different ways. Just want to make sure I've got everything here where I want it. The idea of a stack, I didn't do it the way I wanted it, pardon me. One thing to change. This should be so. Now, the stack is called a last in, first out structure. That's read as last in, first out. What this means is that we are thinking about the stack as having two ends, but only one of the ends is ever operational. Only in one of the ends do we ever do anything. We add to the front of the stack, or I'll say the top of the stack, and we remove from the top of the stack. Technically speaking, we cannot touch any item but the item at the top. Now, you may think this has no use, but it has many uses, and in one of the homeworks you're going to be doing it. I think I may have two of them, two different kinds of examples. One example is to check to see if an expression is legal in terms of balanced parentheses, and we'll look at that. That will be coming soon. But the ADT for stack needs the following operations. We have to be able to push an item onto the stack. We have to be able to pop an item off the stack. We have to be able to get the item at the top of the stack. Traditionally, pop and get are two separate things. Get doesn't destroy it, it leaves it on the stack, it just gives you a copy. And pop doesn't give you a copy. So you got to keep those two apart. They're not one. Then we have to have a is empty. Let me write it this way. And we probably should have an is full if we have restrictions on how big the stack can be. Sometimes we don't have restrictions. The stack is what we view as a container type. The vector is the same, it's a container type. This means that the same functions would be needed if we had a stack of int or a stack of char or a stack of string or etc. There's a way to do this in our coding called a template. And when I start showing you some coding for this, I'm going to try to do that. Right now, I just want you to realize that this is the next data structure we're going to look at. So you can read ahead in the text in this if you want to. We're going to try to implement it in different ways and see how it works. This will end what I'm going to do right now, and I hope that you'll be able to understand this, and if you have any questions, please let me know. Thank you.